Welcome back to my channel. My name is Dr. Anwar Youssef Dunbar, and this is the continuation of my discussion on the exciting science of toxicology. In the first video, I gave a brief description of what toxicology is, and I gave some real-world examples of chemicals that we are exposed to every day, and I closed that video out talking about how chemicals and the various chemicals we're exposed to can exert their functions. So in this video, in this part, I'm going to delve into some of the tools and knowledge sets that toxicologists use when performing their duties, and then I'm going to close this video out by discussing the vastness of the field. So let's talk about some of those tools and knowledge sets. The first one we're going to talk about is the dose response. So this goes back to our key quote. It's the dose that determines the poison. So let's take a look right now at what a dose response is, and specifically what a dose response curve is. So once again, if you haven't, please get the likes up. Please click that thumbs up button, as it helps me and it helps my channel ascend in YouTube's algorithm. So what you just saw was a dose response curve. And so going back to the original quote, it's the dose that determines the poison. Toxicologists are always cognizant of doses. And so typically in experiments, what you'll see, whether you're looking at an effect on a whole organism or an animal or something in cell culture or something in vitro in a 96-well microtiter plate, experiments are usually done over a dose range, going from a low dose to a high dose. And what the toxicologist is looking to determine is where the inflection point is. So typically in classic toxicology, you want a dose where you don't see anything. That's called a NOEL, a no observable adverse effect level, and a low L, which is the lowest observable adverse effect level. And so you want a nice clean dose where there's nothing happening to your subject, and then you want doses where you can see where the effect is starting to take shape or take hold, whichever one. The inflection point, and I learned this from one of the senior scientists where I work right now. She introduced this term to me. That's the part of the curve where the curve starts going up. So you have it flat, you have no effect. The inflection point is where it starts to ascend and you start to see your effect. The effect could be cellular proliferation, it could be cell death, it could be activation of your DNA and all of its downstream or everything that comes after that DNA activation. It could be the activation of a protein in vitro or the inhibition of a protein in vitro. It could be anything, but you're looking for the critical effect levels over a series of doses. That's your dose response curve. And so if your chemical is actually doing something, you should see the effect increase with the dose. And if it does not increase with the dose, then as a scientist, then you kind of say, this chemical is not really doing anything to my system. So it's very critical to understand where your clean doses are, where your effect levels are, and also to know that your chemical or your toxicant is actually causing an effect that is dose responsive. And if it's not dose responsive, if you have an effect over here and over here, but not here in the middle, then you know that it's something else and not due to your chemical. So now I'm going to talk about the 3 routes of exposure, and I'll see you on the other side of this picture here. So toxicologists are always thinking about what the chemical is, what its properties are, and how it's being delivered, and what its mechanism of action is. But toxicologists are always also thinking about what the route of exposure is. So in the case of humans, there are 3 routes of exposure. So before I go into those, let's say the mechanism for toxicity is DNA damage. This molecule gets inside the cell and it breaks DNA strands. But what if the molecule never gets in the cell at all? Then are we worried? Maybe not. So there are 3 routes of exposure. The first of which you just saw in the picture I just showed you, was the oral route. That means you're taking the chemical in through your gastrointestinal tract. It goes to your mouth, your esophagus, and then down into your stomach and your small intestine, and it's may get absorbed from your small intestine into your liver and then into your bloodstream. So it could get into your body that way. And then again, it might not, depending on the properties of the chemical. And that each route has different properties. So the chemical has to go through multiple conditions itself. Your stomach is very acidic, and then your small intestine is very alkali, very basic. And also the oral route gets a certain amount of the cardiac output, or it gets a certain amount of the blood from the heart. It gets about 21%. You can also, depending upon the properties of the chemical, again, you could inhale it, and the chemical could cause some damage in your nasal passage. We call that a portal of entry effect. Or it could go all the way down into your lungs. And if it's, again, depending on the properties, if it's small enough, it could pass through your lung into the bloodstream and then get into your body and into your general circulation there. Now, what's different about the lungs from the gastrointestinal tract, once again, it's the properties of the lungs, but it's also the fact that there's a very small cell layer that separates the lung airway from the bloodstream, which I'll talk about in another video, but also the lung gets approximately 100% of the cardiac output, or the blood from the heart. It all goes to the lungs first before going to the body, because the body needs oxygen. And so if you can get a nice dose into the lung and then into the bloodstream, you can get a nice exposure inside the body, which is very relevant for something like bioterrorism. But a lot of drugs are given through the inhalation route as well, such as aerosols if you ever had a surgery. And then you can get exposed via the dermal route, or on your skin. And the chemical has to have specific properties as well to be absorbed by the skin. It has to be of a certain size, and it also has to be very non-water soluble or non-polar. So something that's chemically neutral and it's small, something like that has the potential to get absorbed through your skin and into your bloodstream. And versus the other 2 routes, the skin only gets 9% of the cardiac output. So it doesn't get as much blood flow as the gastrointestinal tract or the lungs. So with that, I'm going to talk about duration of exposure. So we did the dose response, we did routes of exposure, and now we're going to talk about duration on the other side of this picture. So in addition to dose and route of exposure, depending upon the organism, toxicologists are also concerned about duration. So in some instances, exposure to the chemical to your system could be very quick, or it could be very long. And in some instances, that short exposure could do something pretty damaging. In some instances, not. In some instances, the chemical needs to be in your living system for a long period of time before it really shows a profound effect. In some instances, the effects will get worse with time. In some instances, effects will not get worse with time. And so toxicologists are always thinking about duration of exposure and are the effects getting worse and more severe with time of exposure. And typically, as toxicologists, we think of time in terms of acute, subchronic, and chronic. Acute being hours to a day, subchronic being a month to 6 months, and chronic being a year or more. If I messed that up, you can leave a comment in the description box below to correct me, but I think that's the general relationship. So toxicologists are always concerned about duration of exposure in addition to dose and route. So the last one I'm going to talk about is whether or not the given effect is adverse or not. So I'll see you on the other side of this picture. So what you just saw was a cartoon of 3 sets of cells. And those cells are going to be used to talk about the concepts of adaptive and adverse. And so toxicologists particularly in private industry and in government, in the regulatory sector, they have to figure out whether or not a given effect is adaptive or adverse. And so when we think of something that's adaptive, we think about a given cell being exposed to a toxicant, and that toxicant causing some change in the cell for which it can reverse or go back to its natural state once treatment stops. So in that first row, you saw normal cells. In the second row, you saw cells that were undergoing something called hypertrophy. So we're going to go back to Cell Biology 101. So in some instances, depending on the cell and the tissue type, the cells will react to a chemical by swelling and getting bigger. That's called hypertrophy. In other instances, if you go back to that picture and look at the lowest row, the cells will divide. They'll respond to a chemical challenge by dividing, and that's called hyperplasia. So you have your normal cells, you have hypertrophy, and then you have hyperplasia. Hyperplasia is particularly concerning because it's cell division, and that can lead to something like the formation of a tumor. So let's go whole body here and think about the whole organism. So we know that in a tissue, in an organ like the liver, which usually is the first line of defense when a chemical is ingested orally, We know that the liver cells, they can metabolize or biotransform molecules, and we know that oftentimes the cells respond by undergoing hypertrophy and swelling. Well, in some instances, that's all they do, and we know that once treatment stops and that liver has a chance to recover, let's say recover, we know that those cells will go back to normal and the liver itself will go back to normal. But there are instances where, depending upon the molecule and what it's doing, it could be interacting with DNA, it could be causing some form of cell death, it could be causing these liver cells to create something that's toxic. We know that once those things happen, those liver cells can undergo hyperplasia. And again, that's dangerous because hyperplasia can lead to the formation of tumors, whether it's a benign tumor or a malignant tumor. This molecule, and the liver is just one example, this molecule can get into the body and it can cause, other organs. Let's say it could cause the thyroid to create too much thyroid stimulating hormone, and that can ultimately lead to thyroid cells undergoing hyperplasia. And there are numerous examples of chemicals getting in the body, disrupting certain pathways and causing certain disease states. But they're happening usually, if it's not an irritant or if it's not corrosive, you usually have something happening on the cellular level that's causing something to happen to the whole organism. And we have effects that are either adaptive, which the animal can recover from, or those effects are adverse, which result in more dangerous effects. And it's usually the adverse effects that give toxicologists heartburn, and those are the effects that we really need to be aware of, and those are the effects that we really try to be aware of. So once again, if you haven't, please get the likes up, and please click the like button. In terms of training, once again, I'm going to leave my toxicology blog post in the description box below. But once again, in terms of training, toxicologists usually receive their training in lab settings, either usually pursuing a master's degree or a PhD, and some can even gain valuable experience as bachelor's level scientists. And again, you're usually looking at the effect of a known toxicant down to the molecular level on DNA, and then you could be looking at what it does to a bacterium, a plant cell in some instances, if you're in agrosciences or you're training in that area, or animal cells, if you're particularly training to look at toxicity in terms of human health or some form of animal health. As described in the Michael Jackson example, there's a medical context for toxicology, and it's a very, very vast field. Medical doctors have to learn some toxicology, nurses have to learn some, pharmacists have to learn some, veterinarians have to learn some toxicology. So this is all, it's all in the medical fields. It's everywhere. It's in the chemical industry. There's a whole regulatory sector which employs toxicologists, because again, we have to know what chemicals are out there and what chemicals we need to be concerned about. And anytime a new product is being registered, you have to have toxicologists who are trained to ask questions about the safety of those products. And there are so many different kinds of toxicology out there, and that's described in my blog post, so I'm not going to list those out now. But suffice it to say, there's a whole community of toxicologists out there, and there's a whole society of toxicologists out there, and there's a whole world of toxicology out there. So with that, I'm going to conclude. Please like the video, please share it, and please subscribe to my channel. If you have some comments yourself about toxicology, or if you have questions about something I've said here, or if I've misspoken on something, please leave a comment in the comment section below. Always remember that your attitude determines your altitude. Take care, and I will talk to you the next time. Bye-bye. Okay, I just wanted to come back and say one more thing. As I was rendering this, I saw something that I said, and something I misspoke on, and my colleagues will probably ding on me about it, so I wanted to come back and correct myself. And what I said was, the thyroid creates thyroid stimulating hormone. That's not true. It's the anterior pituitary gland that creates or generates the thyroid stimulating hormone that stimulates the thyroid, and the thyroid synthesizes T3 and T4, which goes into the bloodstream. All right, now we're done. Okay, bye-bye.